Our speaker for today is Dr. Ruta Kale, and Ruta's research is aimed at understanding the physical mechanisms behind the generation and evolution of cosmic rays and magnetic fields on galaxy clusters. And the main field of her work is the diffuse radio emission from galaxy clusters, and is working specifically on the origin and evolution of the non-thermal components, namely the relativistic electrons and magnetic fields in the intra-cluster medium. A few words about our speaker. Dr. Ruta Kale is an astrophysicist working at the National Center for Radio Astrophysics in NCRA at the Tata Institute of Fundamental Research in Pune, in India. She has obtained her PhD at the Raman Research Institute in Bangalore, and worked as a postdoctoral fellow for a few months at the Inter-University Center for Astronomy and Astrophysics in Pune. And from there, continued as a postdoctoral research associate jointly with the Institute of Radio Astronomy and the University of Bologna from 2012 till 2014. And after that, has worked as a postdoctoral visiting scientist at NCRA until 2015, and was then hosted at the NCRA as DST Inspire Faculty Fellow from 2015 till 2020. Since 2017, Ruta is a reader at the NCRA. And let's give the stage to you, Ruta, and thank you so much for being here today for this talk. Hello?
Thank you.
Yes.
Yeah, I hope you all can hear me fine.
Yes.
Yeah.
Yes.
Thank you, Konstantinos. I'm really happy to speak here today, and apologies for the delay. We will do our best now. I will be talking about radio emission and evolution in galaxy clusters. Some recent work which I have done using the GMRT, upgraded GMRT, and the MeerKAT telescope. So I'll be first introducing galaxy clusters in radio bands, and basically what is the nature of intra-cluster medium and what are we trying to study about it in radio bands. And then I'll go over the lessons from radio surveys that have been carried out over the past nearly 2 decades, and then come to the recent work that we have done. So as you all are familiar, large-scale structure of the universe is like a called the cosmic web. Basically, this is a simulation view shown here, which shows the filaments, and at the nodes you have galaxy clusters, and the zoomed in view of the galaxy cluster is shown where you have a central concentration, probably a main central brightest cluster galaxy, and several hundreds of thousands of galaxies are going around in the gravitational potential. And typically these the sizes of galaxy clusters are of the order of a megaparsec. The mass of the galaxy cluster is dominated by dark matter. Only a few percent is in galaxies, and you can see that the major baryonic component of the mass is actually in the diffuse medium called the intra-cluster medium, or ICM. As clusters evolve, they basically grow by mergers of smaller systems, and they accrete mass from these and grow bigger and bigger as time proceeds. And in this process, there are basically processes like shocks and turbulence, which are driven into the medium. And these cause several interesting phenomena in the medium. So what is shown here is a slice from a simulation that includes gas. And you can see how the density, temperature is distributed in these systems, and what it shows up, as markers of turbulence and so on. So in a major merger of clusters, energy, gravitational potential energy of the order of 10⁻⁶3 to 64 erg is dissipated, and it is believed that a fraction of this energy is basically dissipated, converted by shocks and turbulence by reaccelerating particles. And then these reaccelerated particles are what we see as synchrotron emission in radio bands in the presence of weak magnetic fields in the galaxy clusters. Moving on, if you see galaxy clusters across the electromagnetic spectrum, you will see that the two main bands where galaxy clusters stand out or are most commonly observed are the X-rays, where the intra-cluster medium shows up as this big cloud of extended emission in X-ray bands. In optical, you can see the emission mainly from the stars in the galaxies. But what happens if you go all the way down to radio bands, and what happens if you go all the way up in high energy bands to gamma rays? So it so happens that both these bands, gamma rays and radio, are related in some way. So gamma rays, we are mostly at the level of having upper limits. There has been a very weak detection recently in last year or so towards coma. However, the main picture is that we don't see much gamma ray emission from galaxy clusters. So the radio emission from galaxy clusters is allowing us to look at the previous slide, probing cosmic rays and magnetic fields in the intra-cluster medium. And you have relativistic particles and magnetic fields, and these are not detectable in most observing bands, and therefore radio happens to be one of the easiest bands to detect this emission. It is characterized by power law spectra, and the spectral index, the nu raised to alpha here, that's called the spectral index, and that tells you about the radiative age of the plasma. So a freshly accelerated electron population will have a flat spectral index, such as shown here in blue, and an older one will have a steepened spectral distribution, such as shown in red. So measuring the spectrum of this radio emission from galaxy clusters in radio bands allows you to also learn about the age of the electron population and whether or not it is being continuously re-energized or not. Now, relativistic electrons in the intracluster medium can originate from starting from supernovae from the stars in galaxies to AGN, radio galaxy jets. What happens is that shocks and turbulence in the ICM reaccelerates these particles and also create a population of relativistic electrons. And relativistic electrons also happen to be products of hadronic collisions. And also some of the dark matter annihilation models predict a population of relativistic electrons. So we are talking about cluster radio sources that are not associated with particular galaxies, but rather with the intracluster medium itself. These are broadly classified into radio halos, relics, and mini halos. So halos are centrally located, shown here on the left figure. You see in all these figures, contours are the radio emission and color are the X-ray emission. You can see that radio halos are centrally located large sources. Relics are peripherally located and arc-like sources. And mini halos are, you can say, smaller versions of radio halos, but centered around the brightest cluster galaxy, and these happen to be in cool core clusters. Now, these sources are rare. We cannot definitively predict before observing a cluster whether or not a particular cluster will contain such an emission. And that is also one of the things to understand as to which are the clusters where we do find such emission and where and why don't we find that kind of emission. Going to the next. So what is the problem in explaining these radio sources? It is to do with the cosmic ray electron lifetimes and radiative lifetimes and diffusion times. So if you see the cosmic ray electrons over here, the blue curve, you can see that as the energy increases, the radiative losses are basically very high, and over a time scale of a giga-year, you will have most of the electrons losing their energy. There's also inverse Compton process, which takes away energy of cosmic ray electrons apart from the synchrotron emission. And as compared to that, you will see that the diffusion times are really long, more than several giga-years. So the problem is that once a cosmic ray electron is produced, it is very hard to transport it to large distances while keeping its energy relativistic. So certainly radio halo-like sources or even relics cannot be explained by a single source like a radio galaxy, but you need in situ acceleration. Quickly, we will go over some of the plasma properties in order to just place what kind of plasma the intracluster medium is. So these are some basic parameters describing plasma: the Debye length, the electron skin depth, and electron Larmor radius. Now our cluster sizes are of the order of a megaparsec. So, and some basic parameters of electron density, temperature, and magnetic field. We can calculate these values. And what is of interest for us is the electron Larmor radius, which turns out to be very small as compared to the mean free path, which is basically of the order of a kiloparsec. What this means or implies is that once a cosmic ray electron is moving along magnetic field lines, it can go to distances of the order of kiloparsec without getting knocked off the magnetic field line. So the long mean free path means that magnetic fields can actually play a role in transporting electrons in the intracluster medium. One other important parameter of a plasma is also something called as a beta parameter. This is a ratio of pressures. So it's the ratio of the thermal pressure, which can be described by NKT, and the magnetic pressure, which is B squared by 8 pi. And if you do the calculation for some of the standard cluster parameters, you can arrive at a number of the order of 100. So intracluster medium in plasma physics is basically a medium having high beta, which means that the thermal pressure dominates over the magnetic pressure. And in such a plasma, you have many different processes that are happening. So this is a schematic, not all of it is basically, I don't want to read through all the processes, but what I want to show is that we want to learn about all of these processes using the radio emission that shows up in our observations. So it will allow you to probe all of these processes, like the acceleration mechanisms, the turbulence that drives this acceleration processes, and so on. And also in the process, we can learn about the magnetic field. So coming to radio surveys of galaxy clusters, there are typically two different approaches. One is to use all sky surveys and then look at clusters in them, and then extract candidates where you find diffuse emission. And the other way is to go after targeted surveys where you actually find a sample of galaxy clusters and then follow it up in radio bands and so on. So this has been done with the GMRT, also VLA in the past, and there are several surveys now happening as well. So this is a view of the extended GMRT radio halo survey and its mass complete extension. And you can see that it has covered about 75 galaxy clusters across mainly the northern declinations. And we have found some interesting statistics. So this kind of a targeted survey allows us uniform sensitivity over these clusters and also to tailor the surveys to probe specific angular scales given the properties of the radio interferometer used. This was tailored for the GMRT 610 megahertz band, and that is what we found on the statistics. Moving on, we have an empirical scaling between radio power and the mass or X-ray luminosity of the clusters. And if you look at the entire sample, you will see the detections and the non-detections as these arrows in this plot. So there is a large scatter clearly, but there is also a power law that we can describe this relation with. So P 1.4 is proportional to m raised to about 3.9. So the upper limits here are also very important because they tell you about the non-detections and at what level we have a non-detection. And given the complication of observing these clusters with an interferometer, we need to make injections and re-imaging of that from the visibilities in order to come up with these upper limits. So there was a new tool which we had developed a couple of years ago, and if anyone of you are interested, you could take a look at this paper where we tell about this tool called ULCalc. So what this power law also shows that these are transient phenomena having a lifetime of about 0.1 gigayear. The other important thing is the dynamical state of the cluster. Nearly all clusters with radio halos and relics are merging clusters. Here you can see a variety of morphologies in X-ray bands seen with Chandra. And there is a way to quantify the distortion of or the morphology of the X-ray emission via parameters such as concentration parameter and centroid shift. So for this survey, what was done was that you have a plot of the concentration parameter versus the centroid shift, and all these clusters are plotted here, and you can see in red and black the clusters with radio halos and non-detections. So red circles are radio halos. So where you have low concentration and high centroid shift, it means these are merging clusters. So you find more dominant presence of radio halos, whereas mini halos or the smaller counterparts of radio halos in cool cores, you find them in the high concentration parameters and low centroid shift area to the top left. So one interesting thing is that about 90% of the halos are in merging systems. I would say approximately 90%, and 10 to 20% of non-merging systems are actually non-detections. So this is also of interest as to why some of the merging clusters are non-detections, in spite of being just as massive as the rest of the sample. So overall, in this survey, we found that about 70% of the clusters with very high masses, about 8 into 10 raised to power 14 solar masses, are hosting radio halos. And the remaining merging systems that are non-detections are still a puzzle. This picture, this was the largest survey a couple of years ago, and now there are many all-sky surveys like the LOTS survey that is ongoing and has provided very deep images of about, and there are about more than 300 radio halos known now. The understanding of the overall properties has remained similar, though there are several points of interest, but probably that is for another discussion. So we can move to from these surveys that happened over the last 2 decades to something that we did very recently. So most of these surveys were done at less than 1 gigahertz frequency. So the GMRT radio halo survey, which started in 2007, 2008, and then the extended and the mass complete extension of it all the way going to 2021. And there were simultaneously many other surveys that have also come up with many detections and statistical properties of clusters. There have been many deep fields and the LOT survey where new detections have been found. And recently, MeerKAT also has excellent sensitivity to extended emission and it has also thrown up many new detections and very deep images of some of the well-known radio halos. MWA was another southern instrument that also surveyed the sky with a different kind of sensitivity. The resolution was poor, but the surface brightness sensitivity was very good. So they also came up with a sample. So one peculiar thing is that all of these surveys focused on declinations that were typically greater than -30 degrees, especially with the GMRT. LOFAR, of course, is a northern hemisphere telescope. And only recently with MeerKAT and MWA, we have started to explore the southern sky. So a few years ago, we had carried out simulations of radio observations with the GMRT. And we found that even while GMRT can observe up to -50 degree declination, we had confined the surveys to declinations like -30. So when we simulated the UV, the visibilities, you can see the number of visibility points plotted versus the UV distance in kilo lambda for two different declinations, +60 degrees and -50 degrees. And you can see that actually, because of the projection of the baselines that we get when we observe these southern declinations with the GMRT. So these are low elevation observations. So you basically have projected baselines and you actually gain short baselines because of the projection effect. And when we simulated injection of radio halos, sorry, a moment on the previous slide. Yeah, we saw that we could very well recover extended emission in the redshift range of clusters like 0.1 or so. So we designed a survey which was to probe these southern declination massive clusters, which were earlier missed in the samples. So that is what we call the Southern Cluster Scale Extended Source Survey success. So this was a sample of massive clusters extracted from Planck and SPT, the South Pole Telescope catalogs. These are clusters with masses greater than 5 × 10⁻14 solar masses. They're at redshift less than 0.3 and span this declination range. There are 20 clusters in this sample, and they span a redshift range of 0.07 to 0.28. So we had surveyed 9 clusters with the legacy GMRT using either 325 or 610 megahertz. But recently, thanks to the MeerKAT Galaxy Cluster Legacy Survey, we found overlap of this sample with the MGCLS and found 5 of our 9 clusters were covered in MGCLS. And we combined the GMRT and the available MGCLS images to study these clusters. So even before we started the MeerKAT work, using our GMRT legacy GMRT observations at 610 megahertz, we had already discovered a radio halo in this massive cluster. The image on the left is actually showing the radio emission in blue that was detected with 610 megahertz of the GMRT, overlaid on the Chandra image and the optical image. So this was a surprise case because it was not a very prominent merging cluster. So therefore, it was a surprise that we found this radio halo surrounding the BCG at the center of this cluster. So with the MeerKAT, we were able to, sorry, it's fine. The next slide, yeah. So in HST, we could find that there were 2 BCGs very close to the center of the cluster, and one of them was basically having radio emission, compact radio emission. This was a massive cluster, and it was also hot, but not as hot as many other merging clusters. So in the 610 megahertz image on the next slide, we saw the radio halo or a mini halo. That's what we suspected because of the nature of this cluster. Next slide. So here we see the Chandra emission in color, and the overlaid contours are basically point source subtracted image of the radio halo that we saw. So this was the size of the radio halo was very close to what one would call a giant radio halo, but just falling short of it. So we had earlier proposed that this was a giant mini halo. Why we did so was also evident from this plot here of centroid shift versus concentration parameter, where you can see this cluster as a filled star, and it falls in the region which is basically not clearly either relaxed or merging. Thus, this cluster basically showed up as a surprise. And coming back to this slide again, which I had shown earlier, the middle panel is the MeerKAT image, where we have also overlaid the legacy GMRT contours and the MeerKAT contours. So we can see that there is a halo clearly. And in addition, because of the excellent surface brightness sensitivity of MeerKAT, we also detected some other peripheral relics whose nature is as yet not confirmed. We also took uGMRT observations at band 3, and we have made spectral index maps and used band 3 and band 4 data that we had. So here I'm just showing a snapshot of this band 3 image after source subtraction. So we do detect the eastern relic, but the southern relic is still not very well detected at band 3. Possibly it is also a flat spectrum source and probably not related to the cluster, as it is quite far from the cluster, but it may be something like a remnant radio galaxy. But the radio halo is clearly detected, and we found signatures of turbulent reacceleration as shown by typically patchy spectral index. So this was one of the interesting clusters that came up early on from the success survey. To quickly tell you also about the data analysis pipeline that we were developing while this survey was going on, it's called Capture. It's a data analysis pipeline for reducing uGMRT data. So you can basically start from raw data file and come get an image. And it is now working for both legacy and uGMRT data. And we are still making further developments in the pipeline to include direction-dependent calibration and polarization calibration. Polarization calibration, we already have a strategy which we have implemented in the pipeline. And if anyone is interested, they could go and try out this capture poll on the GitHub. On my GitHub account, it is available, and you could try it for band 4 data. I would like to hear about your feedback on this pipeline, because we constantly are in the process of improving it. The other thing I wanted to mention in passing was the use of online RFI excision at the uGMRT. So this is an online RFI filtering scheme, first of its kind, being tested, and it has shown promising results for short baselines, especially given that the GMRT has a lot of RFI at short baselines, and especially for studies of clusters, it matters to observe at short baselines. So definitely, if you're observing with the GMRT, I would also recommend using the online RFI excision scheme. So there were other 9 clusters that we also studied. There was this other cluster, which was a pre-merger. So you can see the X-ray emission here in red and yellow color in the left panel, where you see 2 distinct subclusters connected by a bridge. And there were, in our legacy GMRT image, we found that there was no diffuse emission, but it showed up as basically a non-detection. However, when we followed it up with uGMRT band 3, which was much more sensitive, there is a candidate diffuse emission detected in the region of the bridge. So I've pointed it out with this yellow arrow, because I know that the contours are quite confusing here. So you can see the white contour near the arrow, which is the candidate diffuse emission, which looks like a filamentary source located in the bridge region. So this turned out to be an interesting case of a pre-merger having a diffuse filament on the bridge. There were other clusters where we also ended up with detection. So this was another case where we had only a candidate emission that we detected with the legacy GMRT, but with the MeerKAT, MGCLS paper also reported the detection of this radio halo, and we see we have basically compared the GMRT and MeerKAT images, and this looks like a giant radio halo, again centered mostly around the central galaxy, which is interesting because these are mini halo-like systems which actually have radio extent, which is of the radio halo kind. There were also other interesting cases like this double relic halo system in Able 3399. I won't go into discussing each and every system, but I will just show you these images. So moving on, to summarize, we found also a candidate mini halo in Able 3322 shown in this image here. There were non-detections with the GMRT and also with MeerKAT. So overall, among the 9 that we have surveyed so far, we found 1 radio halo cluster, 1 system which was a radio halo and a double relic system, 1 candidate diffuse emission pre-merging cluster, and 1 mini halo candidate. So looking at the cluster dynamical state and occurrence of these diffuse sources, we again used the centroid shift versus concentration parameters and plotted the types of different radio emission is mentioned in these clusters in the legend over here. So you have this RxCJ0232, which was this cluster which is not clearly a merging cluster, but does show presence of a radio halo. And there are other clusters also which are in this mixed dynamical state, which show presence of diffuse emission. So there are further interesting studies that are going on these clusters to understand the relation between the dynamical state and the diffuse emission in these clusters. So certainly in the southern hemisphere, there is a lot of potential to still discover many new diffuse sources, and it will continue, I think, with the MeerKAT and uGMRT. So moving on to another kind of systems that we are now looking at, the Saraswati supercluster. Can you hold the previous slide? Yeah. So this Saraswati supercluster was discovered by Bakchi et al. In 2017 from the SDSS. So they used the SDSS catalog and carried out an analysis of the distribution of galaxies in it to come up with the discovery of this supercluster. So it is a redshift 0.28 supercluster containing 48 member clusters and 45 foreground and about 185 background clusters in this Saraswati region. Saraswati supercluster is interesting because given its composition, it appears to be a high redshift analog of the famous Shapley supercluster, which is a nearby supercluster. So you can see here the mass distribution of the subclusters. So there is this histogram showing you the number of clusters versus mass. And you can see most of the subclusters in Saraswati are actually low mass clusters. There are 2 dominant systems, Zwicky 2341 and Able 2631, which are the most massive elements. On the right, you can see the galaxy density color plot, which shows the distribution of the Saraswati supercluster. You can roughly call it the distribution of mass, and you can see it is like a filament or distributed in one direction. So we carried out a survey of the Saraswati region with the upgraded GMRT using band 3. And this is the mosaic of the region that we have surveyed. The 2 massive clusters, Zwicky 2341 and Able 2631, are marked here. And you can see these circles mark the Saraswati subclusters, which are basically shown. The symbol size shows 0.5 R200, so it's scaled accordingly. So you can see which are the more massive clusters versus the low mass clusters. So the RMS in our upgraded GMRT images is of the order of, in the range of 36 to 70 microjansky per beam. The beam is of the order of 8 arc seconds. And there is one field where you can see just to the right of Abel 2631, which is of especially poor sensitivity. That is because there is a very bright source in this field, and the dynamic range is limited, and we need to work more in order to bring this field to a comparable sensitivity to others. So this upgraded GMRT survey was further extended to MeerKAT, and we have covered this region of Saraswati with MeerKAT telescope, and we are in the process of reducing the looking at the MeerKAT images, and also some of the fields we may reduce again in order to see if we could get better sensitivity. So today I don't have the MeerKAT results to share with you here, but in future we will be looking at the MeerKAT MeerKAT results in comparison with the upgraded GMRT results. So you can await the results from this. But I wanted to point out one interesting thing that we studied about the brightest cluster galaxies in Saraswati supercluster. So we know that the brightest cluster galaxies host radio emission in most of the clusters where there is cool core surrounding these BCGs. So these are subclusters in a supercluster now. We are looking at the sample of BCGs in the Saraswati supercluster, and we are comparing that sample of BCGs in Saraswati with the sample of BCGs in the Shapley supercluster. So as I've already mentioned, Shapley and Saraswati are basically a nearby and far away systems of superclusters. And what we wanted to compare was whether there is any difference in the occurrence of radio emission in the BCGs in Shapley supercluster versus Saraswati supercluster. So here in this plot, you can see the WISE color basically WISE color plot, which shows the Shapley points in red and the Saraswati points in blue. On the right side, sorry, I need that slide again. So the magenta circles basically here on the blue points mark the BCGs that host radio sources. And the radio powers of these BCGs at the band 3 frequency are in the range of 1.1 into 10 raised to 23 to 2.9 into 10 raised to 25 watts per hertz. And we are also cataloging other member radio galaxies in the Shapley supercluster. But what this color plot here in comparison with Shapley is showing is that most of the Saraswati BCGs are in the range of early type spirals versus the Shapley BCGs, which are mostly spheroids. So this already shows that as we go from redshift of Shapley to Saraswati, are we actually seeing an evolution of the BCGs, that they are spheroids mostly as they come up all the way up to the Shapley redshift as compared to the higher redshift analog, which is Saraswati, where the galaxies are still in the part where they are early type spirals. So probably we are seeing some evolution, but definitely we need a bigger sample and probably deeper observations in order to make further conclusions. There are many other ongoing surveys with the upgraded GMRT. So one of the major surveys that is going on is basically the follow-up of LOT's survey discovered radio halos. So we are doing that follow-up at band 4, and that is actually ongoing. But what I wanted to mention a little more was about the interest in low mass systems like galaxy groups. So there is a sample called XGAP, X-ray Galaxy AGN project, which is a sample of 49 groups which are being observed with XMM Newton. It is a large program of XMM Newton and is the first sample showing very detailed dynamical states of the intragroup medium. PI of this project is Dominique Constantinos here is also involved in this project. So in future, you're likely to hear about this project further. I'm just telling you a little bit about it today. So uGMRT and LOTS observations are already, uGMRT observations are happening and LOTS observations are already available. The motivation to study these groups in radio bands is to basically look at the BCGs, the brightest group galaxies, the BGGs, and if given the sensitivities of LOFAR and uGMRT, whether we could even probe diffuse emission on group scales, which could point out or first manifest the magnetic fields on group scales, which are largely unknown so far. So just to show you a little bit more about this sample, this happens to be a galaxy group sample. If you see the X-ray luminosity versus redshift and mass, you can see these red stars are the XGAP sample, and this is what we have set out to study in radio bands. And actually the observations are happening in this current ongoing cycle with the upgraded GMRT, and there will be more results coming in future. Like I said, this XMM Newton images are providing first very detailed dynamical views, dynamical state views of the groups. Yeah, the next one. So on the left, you can see a group that is less disturbed, and on the right, you can see a group which has a lot of disturbance, and actually the intragroup medium is very elongated. So at this level of detail of dynamical state, we are going to compare the groups and study the radio emission using LOTS and uGMRT. So that brings me to the summary of my talk. So what I told you was that radio surveys of clusters are important to understand the state of magnetic fields and relativistic electrons in the ICM. And starting a couple of decades ago with the surveys like NVSS, one went to make tailored targeted surveys with the GMRT, like the extended GMRT radio halo survey and the mass complete sample. And we have again come back to all sky surveys like LOTS and also the MeerKAT surveys in order to discover new radio halos and relics. And we are trying to understand the current statistics. In the meantime, in the unexplored southern hemisphere is being probed with the GMRT up to declinations of -50 degrees. And the success sample basically is a sample of massive clusters, which we are surveying with the GMRT, and 9 clusters which we have already looked at have been presented in a publication. And there we find already among 9 about 5 diffuse radio emission clusters and 4 non-detections. And there are individual cases of interest, such as the radio halo in a non-merging cluster and a filamentary source detected in a pre-merger cluster, and so on. Survey with the LOFAR, the 144 megahertz LOTS survey, it is transforming our view of the sky and coming up with many new detections of diffuse sources. The interesting thing is now to see the spectral properties of these radio halos detected, and it is going to be a test of the turbulent reacceleration models, which predict that most of the radio halos, or at least half of these radio halos, are expected to have very steep spectra. So only the new observations that are ongoing will be able to pinpoint and either confirm or refute the predictions of these turbulent reacceleration models. The other system of interest are actually galaxy groups, comparing relaxed versus merging groups, and then looking for studying feedback and also presence of large-scale diffuse emission, if any. So in conclusion, many more discoveries of diffuse emission are awaited in the southern sky, and large samples that are now opening up with the all-sky surveys. They have become available, and all of these will uncover the origin and evolution of non-thermal components in the coming days. So I'll stop here. Thank you.
Thank you very much, Ruta. Thank you for this great talk, actually. One moment, let me stop sharing, and yes, great. Thank you so much. If as usual, people, please, if you have any questions, comments, please write them down, or just you can just ask a question. Please, you can do that. In the meantime, let me just maybe kick off with a question. The result for the WISE color plot was really interesting, showing indeed an evolution between the redshift 0.28 BCGs and the ones in the Shapley cluster. May I ask, what would you, because I see that there is provision of sampling as well, the members of the clusters. Would you expect those to fall, let's say, in the same region as the BCGs, or provided that there is maybe pre-processing, or maybe they're falling into the clusters in a different ways, we'll be able to see something more occupying the right side of that plot?
Yes, I think that is correct. I would expect that the brightest cluster galaxies are actually more of this type, and if you go to other galaxies, they will probably turn out to be more star forming, or towards that. So that's what I would expect. So yeah, we haven't yet compared the remaining galaxies apart from BCGs, but it would be interesting. I think what you say is very interesting, to look at any pre-processing and how they have evolved. But it is hard to say whether between Shapley and Saraswati, whether they will show much difference actually.
True. Yes. Thank you. Any questions, any comments regarding the radio emission in clusters? Okay, we have a raised hand here. Yes, Cabello, please, you can go ahead.
Hi, thank you, Professor Kale, for such a very good talk. I think I was a bit distracted when you were talking about the full success sample. I just wanted to confirm how many clusters are there in success. And I think you mentioned that you discovered some with the double relic systems. I also wanted to cross-check how many of those did you discover with the double relics and a halo.
Yeah, so in total, we have 20 clusters in the success sample. And so this is a combination of Planck and SPT clusters. So based on our redshift and mass criterion and the declination range criterion, we ended up with 20 clusters. So far we have finished the survey of 9 clusters. And in that we find 1 radio halo and 1 cluster with a radio halo and double relic system.
All right, thank you so much. And what criteria was used when selecting a sample for success?
Yeah, so these are clusters which are less than 0.3 redshift, and
okay.
They are, so we had used so what happened was, when we selected the sample, there was the Planck release of the sample, and we had the M500 from that release, and there we had put a cutoff of 5 × 10⁻⁴ solar masses. But the masses have gotten a bit revised later on in the Planck catalogs. So the criterion of 5 × 10⁻⁴ in that Planck release and the new ones is, we ended up with a couple of clusters which were slightly below 5 × 10⁻⁴ solar masses, with the new better estimates of the mass. But overall, they were selected with the criterion of greater than 5 into 10 power 14 solar masses. And then the declination range of -30 to -50 degrees.
All right, thank you so much. If I can just have one more follow-up question. For the 9 that are observed, is the data publicly available?
Sorry, which one? For the?
You said you've observed 9 out of 20 success clusters.
Yes.
Is their data available to the public for use?
Yes. So all the GMRT data are public. The upgraded GMRT data were taken more recently on the specific targets. So the pre-merger cluster that I showed where there was a radiofilament detected, that observation, I'm not sure, it may or may not be public as yet, because we did the observations recently like a follow-up. So the follow-up observations, I think only for RxCJ 0232 are public. The others, I'm not entirely sure, but the ones which we had taken as a part of the survey with the legacy GMRT, those are all public.
All right, thank you. And how many of the 20 are cross-matched with MGCLS?
5.
5, okay, thank you so much.
Thank you. Any other questions before we thank our speaker? No, maybe.
I see Paul.
Okay, sorry,
raise
I
hand.
just missed that. Sorry. Yes, please, Paul, please. You may.
I think
Yes.
they're unmuted, but I can't hear them as yet.
We cannot hear you, Paul. Can you please? No, we cannot hear you. Maybe if you could just write down your question, or apologies for that, we cannot hear you. Okay, 1 second. Not sure if we can hear you, but yeah, it's not working actually. Yeah.
Oh, okay.
It's
we can
your
hear you. Yes. Hi.
well, actually, it's the me talking. I was actually trying to help diagnose. I just wanted to find out if his what device's microphone is on. Sometimes Zoom is on, but then the device's microphone is off. Yeah.
Yes. Thank you, Sam. Yeah.
Yeah, you're welcome to email in case it doesn't work here.
Or at least you can write down, and I can just say it and have it as a last question. Yeah. Thank you so much. What have the cluster?
Okay.
Yes, a question from Paul Fallon. What have the cluster service informed us about the magnetic fields?
Yeah, so there are basically these radio surveys which we do in continuum, and there are other radio surveys of clusters which have basically looked at background polarized sources and tried to find out the line of sight magnetic fields. So what we know from the surveys which try to measure the magnetic fields using background polarized sources, where the samples are basically very unbiased towards any mass or typically mass or any other dynamical state. So those have shown that magnetic fields of microgauss levels are present in all the clusters typically. However, from our radio surveys, like what we do in continuum, we know that even in presence of magnetic field, the presence of diffuse radio emission is not common. So what it points out is that the relativistic electron populations may not be similar across all clusters. So there must be something that probably merging, like shocks and turbulence. So it is reaccelerating particles to generate this synchrotron emission. So the presence of synchrotron emission basically is trying to tell us that the presence of relativistic electrons is probably being influenced by factors which are beyond what decides the magnetic fields in clusters. So magnetic fields we know are common in all clusters, but not the diffuse radio emission. So you need relativistic electrons. And currently the understanding is that for these acceleration mechanisms, like be it shock acceleration or turbulent reacceleration, you need a seed relativistic electron population. And that may not be present in all clusters. So although magnetic fields are, in order to cook a halo, you also need relativistic electrons. And that has to come from some fossil relativistic electron population, which may be coming from either reacceleration of seed particles from radio galaxies and other processes which generate relativistic electrons, but not enough for a halo. So we have learned that we know from many different observations that magnetic fields are common in clusters. But what we learn from our surveys is that presence of relativistic electrons may not be as common. And that may decide whether or not, at what level you see the radio emission, like we see in the form of radio halos and relics.
Thank you. Thank you. And if we do not have any further questions, thank you from all. Okay, let's thank our speaker for today. Thank you for this wonderful talk, Ruta, and wish you all the best. Okay.
Thank you.
Bye.
Bye.
Goodbye to everyone.
Bye. Good evening.
Bye.